We have covered the forward mode and the reverse mode automatic differentiation. Now we can jump into automatic differentiation for physical simulations. There's a great demand for gradients in physical simulations. For example, if you want to solve a nonlinear equation, you might use gradients or derivatives in a Newton's method. You also need gradients for uncertainty quantification to do sensitivity analysis. And in inverse problems, usually you want to formulate your problem as, for example, a PDE constraint optimization problem. And to solve those kind of problems, you also need to calculate the gradients with respect to your free optimization variables. So we want to make the problem more concrete. Let's consider a bar and heating with a source function fxt. The right-hand side of the bar, the right-hand side of the bar has a fixed temperature, which is 0 here, and the left-hand side is insulated. And we can use a partial differential equation to describe this physical process. And the main governing equation is the heat diffusion equation, as you can see here. And this is the Laplacian operator. And the kappa is the so-called diffusivity coefficient. And in our case, we would express the kappa x as a spatial varying function, which has this form. This is linear in the location. Of course, this is an ideal model, and you can custom this model in real applications to different kinds of functional forms. And you have the right-hand side is a fixed temperature, and the left-hand side is insulated. So this is a graphical illustration of the equation, and our goal is to calibrate those parameters in the diffusivity coefficient A and B. We need to measure the temperature at some locations. For example, in the laboratory, we can just place a sensor on the left-hand side and measure the time series of the temperature. And we want to use this data to estimate the A and B. How can we do that? The way to do that is to formulate the problem as a mathematical optimization problem. And this is actually a PDE constraint optimization problem. You want to minimize your solution U0t given a specific A and B, or given a hypothetical or candidate A and B. Then you have a solution here. You want to minimize the discrepancy between your hypothetical U0t and your observation U0. So this is the mathematical formulation. You can just do the integral over time, or in the discrete subformulation, you can just do least square, square sum of the discrepancies, and also the constraints. And the constraints is actually the PDE. I just copied the PDE here, and this is the standard PDE constraint optimization problem, where you minimize the objective function with the PDE as the constraint. So how can we solve that? One way to solve that is to discretize the PDEs and also the objective functions. To discretize the PDEs, you might employ some numerical solver. And here we consider the finite difference solver. And to discretize this formula, you can discretize every component of the partial derivatives using finite difference. And you have this part, and also you have this part for the Laplacian. And the kappa I is actually, you plug xi into this formula, and then you get a point value at each location. Okay, so and this is for the governing equation. Also, you have the initial and the boundary conditions. You can discretize the boundary conditions as follows. You have this insulated boundaries. Like here, I use the so-called ghost node, because at this point you can express the gradient just using forward difference, but here I use central difference. There's just a very small difference using two different formulations. Also, you have the boundary conditions on the right, and also this is the initial conditions. I assume that it is the initial conditions is 0 everywhere. Okay, so we can rewrite everything in a linear system where you have a matrix A times U. U is the vector of the solutions, and you just place U1 and U2 and U2 Un as a vector, and you can write in this very clean form. And you also have the lambda I, and the lambda I is I think this is a typo here. This should be a plus sign, and you have this AB and also FK, which is the source function. So then we just cast our continuous PDE constraint optimization into a discrete one, and we want to minimize the discrepancy between your solution and also the observations. And also the constraint is expressed by this algebraic linear system. And we can construct a computational graph for that. That's where AD can help us. When we construct a computational graph, and you can see that at every column is corresponds to a single time step, and A and B, because A and B is in this matrix, so that means the A and B, the primitive variables, will have an edge connected to every time step. And finally, for this node, this is the objective function node. And for the objective function, it will take values from the output of U1, which is the first output of each time step, and aggregate them and outputs the total discrepancy using square sum. And this is the computational graph for the computation. So as long as we formulate the computational graph formulation, then we can just throw it to automatic differentiation software, and it will find us the gradients with respect to A and B. So this is how we can implement this function and this computational graph in ADCME. And you will have a chance to practice that in your homework. And also I will give you more details in the next lecture.